Alright, today we're going to talk a little bit about confidence intervals, and I'm going to give you a number of examples. And so let's start out with, I'm going to bring our old friend back here. Well, we'll just cover this up for now. So we're bringing our old friend back, and we can see from this video or this animation, I can make a custom, whatever I want, type of distribution. I can animate it, and I'm going to get the mean of samples of 5 from this. So I'm animating it, getting the mean. I'm going to do that 5 times. I get 5 different means. If I do it 10,000 times, well, I get this kind of a little bit of a skewed mean here, but then it's a pretty skewed distribution. In fact, anything I have, let's see, let's try a very different one. So we'll animate it. We've got our mean again. We'll do that 1,000 times, we'll do it 10,000 times. And you can see whatever the weird kind of distribution I have, I start getting something that looks like a Gaussian curve. And if I take more samples at a time, it'll actually turn out, you can see this is 5 samples at a time, and I should be getting, oh, always forgetting to do that. Okay, so we'll do 10,000. You can see that the more samples I take at a time, that the more it turns out have a tighter, in fact, the sigma, you can say the sigma of the sampling means is always equal to the standard deviation divided by the square root of n. And obviously, the bigger that n, the tighter the distribution is going to be. Now, why am I talking about that in regards to the sampling distribution? Let's pretend, or the confidence interval. Let's pretend we've got something like this curve right here, which you can see arose from samples of 25, and those were we just got a whole bunch of x bars. So we've got these x bars, and they turned out to have this distribution that looked kind of like this. Those were our x bars. And we know that the standard deviation from the means is just standard deviation divided by square root of n. And let's say that we wanted to know what is our intolerable crap level. Well, we'll call that intolerable crap level alpha. And alpha we probably want to be pretty small. 5% is usually a good number. 1% might even be better. And what we often do, since we don't want to use intolerable crap level when we're speaking to the public, we use instead the polite term, which is the level of confidence. In other words, 1 minus alpha. This is the good stuff. So if alpha was like 5% of intolerable crap, then that would mean 95% of that we were confident in. And this 1 minus alpha is often also called the confidence coefficient. Oops, if I could spell. Okay, so if that's the case, then let's say that we had an alpha of something like 5%. So alpha is 5%. Well, alpha means intolerable crap level of 5%. Well, that means we have to distribute half of it on either side. So this area would be alpha over 2, and that area would be alpha over 2. And so obviously this is going to be, if alpha was 5, alpha was 0.05, then alpha over 2 is going to be 0.025. And this will be 0.025. Well, how can we figure out what sample mean we would get that would be right at that edge of the confidence interval that we're interested in? We can do it. You know already, or you probably have a feel for the idea that if we can just find the z-score that's at the edge, we're in. We would be able to figure that out. So we can figure out what that z-score is, and here's how we would do it. We would say, well, we always know that z is equal to x bar minus mu divided by sigma with square root of n. And remember, that just means how far is our sample mean from the true mean normalized with our standard deviation from the means. That's our z-score. So if we want to figure out what that z-score is right at the very edge, we're basically looking for, on this left side, we're looking for the low z-score, where z of an area of alpha over 2. We want that to be less than the normalized, or be the lower boundary of the limit of this normalized distance from the mean. And on the upper side, it can be z alpha over 2, range up to a z of that value. And essentially, the probability ranging between those numbers, those z-scores, should be equal to our confidence coefficient. So we can rewrite this if we want and say we're looking for the probability that we can go that far below the mean. Remember, we're sort of expecting that our x bar is right around the mean. It's less than the mean, and then is less than x bar plus z alpha over 2 sigma divided by the square root of n, and all of that should be equal to 1 minus alpha again. So what's the case? Then the 1 minus alpha, well, we can call it 100 times 1 minus alpha to make it into a percentage, confidence interval is going to be, well, it's going to extend on the lower side to be to this extent, and on the upper side to this extent. So the whole confidence interval is going to be 2 times z alpha over 2 sigma over square root of n. Now, the error is equal to basically how far away we can get from the mean. And if we want to restrict our error, what we can do is we can say that essentially we can be 100 minus alpha, or times 1 minus alpha, percent confident that the error will not exceed a specified amount E when the sample size is, well, let's see, if we look up here, we can say the error is Z alpha over 2 sigma over n, right? So all we have to do is just rearrange this, and we can say that the sample size would need to be Z alpha over 2 sigma E squared. I think I put something exactly like this on my final last time. So how can we understand what all of this means? First, let's go, we'll take, there's this example in your book, the first one in chapter 8, and we're going to take that example and we're going to build on it a little bit. First they do a Sharpie V-notch test on 10 samples, and what they find is that on average the samples need 64.46 joules break for those 10 samples, and they have a sigma of 1 joule. And if we wanted to, let's say I said find the 95% confidence interval for mu. Well, let's see. If we go and take a look at the z-score for z is equal to 0.025, and that's 1.96. So we can then say, well, I can show you, I'm going to pull this up momentarily. We're looking for a z of 0.025, so let's go look here and see if we can find 0.025. Here we go. It's right here, and a little trouble with my inking, but you can see that's at 1.9, and up here it's got a 6, so it's at minus 1.96, and that's where we got that 1.96 from. Then we can say x bar minus z alpha over 2 sigma over square root of n is less than mu is less than or equal to x bar plus z alpha over 2 sigma square root of n. Okay, that's what we're dealing with. So then we can say 64, if I'm actually plugging in 64.46, that was our average from right up here, minus, and then we have the z-score, which is right there, so it's 1.96, 1 over the square root of, well, 10, because we have 10 samples, is less than or equal to mu, is less than or equal to 64.46 plus 1.96, 1 over the square root of 10, and when you add that all up, 63.84 is less than, mu is less than 85.08. So if that's the case, then what we can do is, well, we know that we're fairly confident, in fact we're 95% confident that 95% of the samples that we would take would have a mean that would fall within these limits. Now, I know what you're really interested in is, okay, we get this. This is all easy stuff. What are you going to put on the test, right? So let's see what I can put on the test. I could put something wacky. I could say, but what if I wanted to know the 80% confidence interval? Oops, confidence interval. See, because if I asked a question like that, then, well, that's not a usual question, because we usually want to know 95 or 99, and if I ask 80, then you'll know, then I know you really know how to get it. So that means our level, our unacceptable crap percentage is actually 0.2. And because 1 minus alpha is 0.8, right? So if that's the case, 0.2, okay, now we draw our little chart. We got that. Now what we want is we want to have an area of 0.1. 0.1 on either side. And what I will do is to magically bring this on your screen so now you can see the page from your book. So I am looking for, if you'll remember, we are looking for alpha over 2 is supposed to be 0.1. So we're going to look over here to find an area. That's the area of this little thing right here. We want that area to be 0.1. So we're looking around here. We seem to find something right around here. That's pretty close to 0.1. And that is read at minus 1.2. And then we go up here for the final digit. So it'll be minus 1.28. That is the z-score. Once I've got the z-score there, I can say, now I can plug back in, and I'll say 64.46 minus 1.28 over 1 over the square root of 10 is less than or equal to the mean. It's less than or equal to, oops, I didn't do this very well, so 64.46 plus 1.28, 1 over the square root of 10. And this number, as it turns out, is about 4. And this number, of course, is also about 4. So we can say 64.46 minus 4 is about 60.46. And well, that's supposed to be less than or equal to the mean. And that's less than or equal to, in turn, 68.46. So the 80% confidence interval is given by this right here. And now, no matter what kind of wacky confidence interval I might throw at you, I do like the number 73, you should be able to calculate it. Okay, one last little thing I want to show you. This is from Online Stats book, which is, I believe Rice does this set of simulations. And what's nice about this is where I'm pulling up. When I click sample, it's going to take 100 samples of the specified size. So if I say we're going to take 10 apples out of the bin, for example, that's what this 10 will be. Now I'm going to get 100 samples. In other words, I'm going to get 100 sample means. Now, so we'll take a sample. Now notice how each of these, it's supposed to have the actual mean is 50%. But you can see each one of these, I wish I could draw on this, but I don't think the pen is going to let me do that. No, when I do that, it goes away. Okay, so just pretend that on the top of each one of these is a bell curve. Right? And so you can see this bell curve got way off. In fact, it's all the way outside and away from sample mean. We don't even contain it in there. So that's what they're talking about here. They say if the 95% confidence interval contains the population mean of 50, then the line will show the 95% confidence interval in orange. So that's what most of these are. The 99% confidence interval is that little blue part at the edge. If the 95% confidence interval does not contain the population mean, then it will be shown in red. There you go. There's some red ones. And every once in a while, if the 99% interval does not contain the population, that will be shown in white. So you can see there's two within this whole set of 100 sample means that did not contain 50 within it. Then we had 6 of them that didn't have the mean of 50 fall within the 95% confidence interval. So let's try a sample size of 20. Let's see. Oh, we've only got one that fell, or no, is that right? Yeah, only got one. It shows 3 here, but I don't see 3 here. But you can see how what this is actually meaning is that the probability in general that we'll have all samples will contain the true mean is given by, well, we can visualize it right here, how it would fall out. Let's do one more. 15 sample. Yep, we got 1 out right there. 20 sample. Seems to like 3 even when there's 2. Not sure how that is working.